This is lecture 4C. Last time we introduced crystal field theory in order to try to predict properties of coordination complexes. And crystal field theory assumes that the ligands in a complex actually affect the d orbitals on the central metal, and they cause the energies of the d orbitals to split apart into different levels to break the degeneracy of those. And we're going to talk about an octahedral complex today, and it's going to have a transition metal that has 6 d electrons in it. Normally, the d orbitals in the transition metal would all have equal energy. They would be degenerate. The 6 electrons would go 1 in each of the 5 different orbitals first till they're all unpaired, and then the 6th one would pair up. But when the metal is surrounded by ligands in an octahedral field, those 6 ligands are going to have lone pairs that repel against those d orbitals, causing some of the d orbitals to be more stable and other d orbitals to be more unstable. And so a splitting occurs between the dxy, dxe, and dyz orbitals, and then the dx squared minus y squared and the dz squared, which actually repel more by the ligands, so their energies are going to be higher. So what we want to do is we want to try to think about how would the 6 electrons in the transition metal go into these d orbitals if the energies are not all the same. And if you have a really big splitting energy, that just means the bottom 3 orbitals are so much more stable that the electrons are going to stay in those orbitals first and fill those completely before they even think about going up into the 2 higher energy orbitals at the top of our energy diagram. So with 6 d electrons in a diagram like this, in an octahedral complex, where the energy between the 2 sets of d orbitals is really large, the first 3 electrons will go into the bottom 3 orbitals, and then the final 3 electrons will also go in the bottom 3 orbitals, like this. Now, there is some repulsion occurring between electron pairs, but that's minimal compared to having to put an electron up into either the dx squared minus y squared or dz squared, where it would be much more unstable. If the arrangement of electrons in an octahedral complex like this has all the electrons in the lower d orbitals, we call this a low spin complex. This is a complex that is resulting from a large splitting energy. So the electrons remain in the lower d orbitals, and this produces, and here's where the word low spin comes from, it produces a low number of unpaired electrons. Notice we have no unpaired electrons here. Why is that significant? Because unpaired electrons is what produces the property of magnetism. If materials are permanently magnetic, that's because they have unpaired electrons, and an entire piece of a material will actually have these unpaired electrons spinning in the same direction, creating a magnetic substance. Iron's a good example of that. Those types of materials are called ferromagnetic. Other things will have unpaired electrons and will only become magnetic if you put them in a magnetic field. Those are called paramagnetic. But if you have a material with no unpaired electrons at all, we would call that diamagnetic, and that's what's happening here. Because of the large splitting energy, the d electrons are all paired in the 3 stable d orbitals, causing the complex to be diamagnetic. Now, what if the splitting energy was not large? What if the splitting energy was small? And you have 6 d electrons. Well, now the six electrons may actually go 1 electron in each of the 5 orbitals first before the 6th one finally pairs up. So with a small splitting energy, you actually don't have the entire lower level filled first. It's actually better to minimize electron repulsion, and the electrons will actually spread out like this. In an arrangement where you're using both the high and low energy orbitals to spread the electrons out, we call this a high spin complex, which is a complex that has a small splitting energy, resulting in the electrons distributing into all 5 of the d orbitals, and it produces, here's where the name comes from, a high number of unpaired electrons. This particular arrangement has 4 unpaired electrons, which means this complex would actually be paramagnetic. Because it has unpaired electrons, it'll become magnetic in a magnetic field. So because of the small splitting energy, the d electrons remain unpaired as long as possible, causing the complex to be paramagnetic. So depending upon what the splitting energy is, you may have substances be paramagnetic or diamagnetic. The electron structure is directly related to what that splitting energy is. And the splitting energy, which here is graphically represented by the arrow, it's labeled delta sub O, which means the splitting energy of the octahedral complex, O for octahedral. This splitting energy depends upon two things. The first is the charge of the metal. The greater the charge, the greater the splitting energy is going to be. So the greater the charge of the metal ion, the larger the splitting energy. But a second thing that affects splitting energy is the ligand that's actually attached to the metal. The ligands can either be what we call strong field ligands or weak field ligands, and that will determine whether the splitting energy is large or small. And let's go through these two different types of ligands. Now, to understand how you can have strong or weak field ligands, we have to understand how the ligands bond to the central metal. And that was first proposed in 1960 by Leslie Orgel, who proposed a theory explaining the bonding that occurs in coordination complexes, and we call that today ligand field theory. It assumes coordinate covalent bonding between the ligands and the metal using molecular orbital theory. So a couple things in here: molecular orbital theory from Chem 1A, covalent bonding from Chem 1A. What's a coordinate covalent bond? Well, let's go back to covalent bonding. Let's say two hydrogen atoms are going to bond together to form an H2 molecule. What type of bond exists between them? We would say a covalent bond, because those two electrons you see would be shared. And when they share the electrons, that's what covalent bonding is, the attraction of two atoms by shared electrons. Now, specifically what's happening, those electrons on those two hydrogen atoms are in 1s orbitals. So as the hydrogen atoms come together to make a bond, where do those two electrons go? We need to look at pictures of the 1s orbitals to understand what's really happening. So the yellow hydrogen there represents its 1s orbital with one electron, and the reddish orbital represents the second hydrogen, its 1s orbital with one electron. As the hydrogen atoms approach each other, those two atomic orbitals will merge together to form a new orbital that's called a molecular orbital. The two electrons will go into the molecular orbital, and if you notice in the picture, you can see in the middle there's a really darker orange region that's representing a higher probability of finding the electron in that spot. Well, you actually have a high concentration of electron probability in the region of space between the nuclei of the two atoms. That negative charge that's in the middle there attracts the two positive nuclei, holds the atoms towards that negative charge, that bonds the atoms together. That's what a covalent bond is. Molecular orbital theory says that when atoms bond covalently, their atomic orbitals overlap with each other, they merge together, and they change from atomic orbitals into a molecular orbital, and two electrons in a molecular orbital constitutes a covalent bond. Now, what's a coordinate covalent bond? Well, that's a little bit different than what happened here between the two hydrogens. When the hydrogens created the molecule, the bond was formed by one electron from the left hydrogen, one electron from the right hydrogen. But a covalent bond doesn't have to be that way, and a coordinate covalent bond is a covalent bond in which the two shared electrons just happen to come from the same atom. Still makes a covalent bond. It's no different. It's just we're indicating that this bond was created from one atom that had two electrons and the other atom that didn't have any. And this is the type of bonding that's found between ligands and the metals in a complex. A ligand will have lone pairs in outer shell orbitals. A chloride ion may have a pair of electrons in a 3pz orbital. And if a metal with its d orbital approaches the chlorine and these two overlap with each other, then the metal's d orbital and the chlorine's p orbital can merge together to form a bond. But where do the electrons come from? They both come from the chlorine, and so therefore this would be called a coordinate covalent bond. Now, coordinate covalent bonding leads us to a final topic in general chemistry concerning properties of acids and bases. It turns out that coordinate covalent bonding is an example of a Lewis acid-base reaction. So we've spent a lot of time in general chemistry defining what acids and bases were, and way back in Chem 1A, the very first definitions, late 1800s, of what acids and bases were came from Svante Arrhenius. Arrhenius said that an acid is any substance that releases hydrogen ions into a water solution, and a base is any substance that releases hydroxide ions into a water solution. Those are certainly true statements. but that definition did not encompass all substances that we know that can be acids or bases. Something like ammonia, for example, NH3 is a base, but how could that release a hydroxide ion? It can't. There's no hydroxide in its formula. So Arrhenius's definition was a little bit too specific. So that's when Bronsted and Lowry came along 30 years later, and they expanded the definitions of acids and bases. And they said, no, an acid doesn't just release a hydrogen ion, it donates a hydrogen ion. And a base is something that accepts a hydrogen ion. And that explained why ammonia was a base, and that actually encompassed a lot more types of compounds. But there's other things that can be acids or bases, but they don't even have hydrogens in them. And how can that be? Well, we need to broaden the definition one more time, and that's what Lewis did when he proposed an even more expansive definitions of acids and bases. Lewis said that an acid is an electron pair acceptor. So make sure you get this right. The Bronsted-Lowry definition was a hydrogen ion donor, but a Lewis acid is an electron pair acceptor. And if a Lewis acid is an electron pair acceptor, what's a Lewis base? It's an electron pair donor. So let's look at an example of a Lewis acid-base reaction that doesn't even involve hydrogens at all, because a Lewis base just has to have a lone pair or a pair of electrons that it can donate to make a bond, and the Lewis acid needs to be able to accept that electron pair. No hydrogens are actually necessary. This compound, boron trifluoride, is a molecule that exists. The boron does not have an octet configuration because it's hypovalent, doesn't have enough electrons to make an octet, but it still exists. And this compound, nitrogen tribromide, has octets for all of its atoms. If these two compounds interact with each other, they will bond. And can you see how that bond's going to form? The nitrogen has a lone pair in its outer shell. The boron has an empty valence orbital, so the two electrons from the nitrogen can be donated to the boron to create a bond. So what's happened here is the BF3 has accepted an electron pair. It's a Lewis acid. The NBr3 has donated a lone pair. It's a Lewis base. And this is the type of bonding that we believe happens in coordination complexes. If you have a central metal like an iron positive 3 ion where it's lost its valence electron, so it has no valence electrons, and a ligand comes up to it with all these lone pairs on it, the ligand can use one of its lone pairs to donate to the iron in order to bond. So the iron, the central metal, is the Lewis acid because it's accepting an electron pair, and the ligand, the fluoride, is donating an electron pair. It's the Lewis base. So from these two examples, there's something you can clearly recognize that will allow you to identify whether something's a Lewis acid or a Lewis base. A Lewis acid always has an incomplete outer shell or an empty valence orbital. That's why BF3 is an acid. It didn't have a complete outer shell for the boron, so it could accept an electron pair. And then if you ever have a cation, like a sodium ion, magnesium ion, aluminum ion, iron ion, they will always have holes in their outer shells. They can accept electron pairs. They're always Lewis acids. A Lewis base will always have to have a lone pair in its outer shell available to make a bond. That would be like NBr3 or any anion. Anions always have octets with lone pairs in their outer shells. Chloride, sulfide, nitrite, carbonate, these would all be examples of Lewis bases. One other example that's a Lewis acid-base reaction is one that you may not think about would fit into this category, but actually is the reaction of carbon dioxide with water. We know that on Earth, all water has a pH that's slightly acidic, even though water should theoretically be neutral. And that's because there's carbon dioxide in the atmosphere. It dissolves in the water. And when carbon dioxide and water react, they form carbonic acid. This is a reaction that occurs between any non-metallic oxide and water. Sulfur dioxide would react with water to make sulfurous acid. Nitrogen oxides would react with water to make nitric acids. It's a typical reaction that occurs. Notice the formula or the structure of the acid. It looks like it's hydrogen carbonate. You have the carbonate ion, and a pair of the hydrogens are attached to the oxygens. Well, how did this carbonic acid molecule get formed? The carbon needed to form a bond to a third oxygen. How's carbon making a bond to a third oxygen? It's using this lone pair. This lone pair bonds to the carbon here, creating the molecule. So this is a Lewis acid because it's accepting a lone pair. This is a Lewis base because it's giving up a lone pair. So now, when we get to ligands, ligands are either going to be strong field ligands or weak field ligands, and let's look at the difference between them. Strong field ligands are ligands that produce coordinate covalent bonds between ligand orbitals and the metal d orbitals that causes a splitting energy to be large, and we've got to see how you make splitting energies be really large. Let me give you 3 examples of strong field ligands: the cyanide ion, carbon monoxide molecule, and the nitrite ions. They're all strong field ligands. Now, let's take carbon monoxide as an example. How does a carbon monoxide molecule bond together? It exists with a triple bond. The only way to make octets for the 2 atoms is to share 3 pairs of electrons. So how does this actually form? If you think about it, you've got to predict what hybridization each of the atoms would be creating in order to bond. The steric number of the carbon is 2 because it has a lone pair and an oxygen bonded to it. The steric number of the oxygen is 2 because it has a carbon bonded to it and a lone pair. Steric numbers of 2 are atoms that always undergo sp hybridization. So their normal valence orbitals, the s, the px, the py, the pz, get morphed into a pair of sp orbitals which point linearly, and then 2 unhybridized p orbitals that are left over. So if we look at the arrangement of the sp hybridized orbitals in a carbon atom, you have, pointing to the right, a red sp hybrid orbital, pointing to the left, a yellow sp hybrid orbital. Those are the 2 hybrid orbitals created. And what was not hybridized are the orbitals left over, a 2pz in purple on the z-axis, and a 2py in orange pointing directly towards you and going back. The oxygen is sp2 hybridized as well, so its orbitals are going to look exactly the same. So let me draw an oxygen with the exact same orbital arrangement. So how do these atoms bond? As they approach each other, the red orbitals will overlap to create a molecular orbital. The sp orbital on the carbon and the sp orbital on the oxygen combine together, and those 2 red orbitals merge together to make a molecular orbital, and that's a bond between the 2 atoms. Now that's one bond. Where are the other bonds coming from? Let's draw my little diagram here in stick figure picture. If I draw my original carbon with its sp orbitals as the lines pointing to the right and the left, the lines pointing up and down are the 2pz, and the wedge in the dotted line is the 2py. So this is just a stick figure representation of an sp hybridized atom. The oxygen I would draw the exact same way, and one bond that gets formed is by having those 2 sp orbitals pointing directly at each other, and you can see them right here. That's creating a covalent bond between the 2 atoms. Where are the other bonds coming from? Well, they're coming from the p orbitals, which are parallel to each other, the purple ones that are parallel up and down, and the orange ones that are parallel coming towards you and going back. So if the p orbitals overlap a little bit on the top and the bottom, that constitutes a second bond. If the p orbitals on this axis overlap in front and behind, they constitute a third bond. So in our stick figure on the left, if we overlap the p orbitals on the z-axis, that's bond number 2. If we overlap the p orbitals on the y-axis, that's bond number 3. And what are the final 2 orbitals going to be doing that are pointing to the very left and the very right? Those are going to hold lone pairs. So the lone pairs go there. This is how this ligand molecule, carbon monoxide, is bonded together. Now, let's apply molecular orbital theory to this. I want to focus in only on my purple molecular orbital that I have in my picture. That's the combination of the 2pz on the carbon and the 2pz on the oxygen. Those are atomic orbitals, 2pz, 2pz, and they merge together to make this purple molecular orbital. The picture I have of that purple orbital there is kind of a cartoon picture. It actually more looks like this. You have a region of high electron probability above the internuclear axis and a big region of electron probability below. Here's an important point from molecular orbital theory. If you're going to take 2 atomic orbitals, a 2pz and a 2pz, and combine them to make a molecule, if you're starting with 2 atomic orbitals, you have to end with 2 molecular orbitals. And right now, I'm only showing you 1, and that's because this is where the electrons go. But there has to be another orbital that's created. What's that other orbital? Well, what do we call this orbital we've just made? That's called a pi bonding molecular orbital. When 2 atomic orbitals merge, they always form a bonding molecular orbital. But if they combine their wave functions in a different fashion, they will form something different that's called an anti-bonding orbital. So another orbital is also created in this molecule. It just doesn't have any electrons in it. It's an orbital that looks like this, and that's called a pi anti-bonding molecular orbital. So anytime you have ligands that have double bonds or triple bonds, you will always create the pi bonding molecular orbital, which will be filled, and then you will also create the pi anti-bonding orbital, which is empty. So how does that anti-bonding orbital play a role here? Let's go to the metal now. Let's take one of the metal d orbitals. And which orbital would this be? The lobes are not pointing on any axes. They're pointing into the quadrants, right? So this would either be a dxy or a dxz or a dyz. But it can't be the dx squared minus y squared. It can't be the dz squared because those two orbitals have their lobes pointing right on the axes. So let me just say this is the dxy atomic orbital. Well, as the metal and the ligand approach, the red and the blue orbital are going to overlap, and the two electrons in the metal d orbital can then go into the anti-bonding orbital, creating a coordinate covalent bond. That means the electrons now will be near multiple nuclei instead of just the metal's nucleus, and that's going to make them more stable. That means the energy of the dxy is going to go down. And that's what would happen to the dxz and the dyz as well. We have a name for this type of bonding. It is a coordinate covalent bond, but it's also called back bonding, which is just a coordinate covalent pi bond formed between a d orbital of a metal and an empty anti-bonding orbital of a ligand. And the significance of this is this causes the dxy, dxz, and dyz orbitals to become more stable because their electrons are now near the nucleus of the metal and the carbon and the oxygen, causing more attraction and therefore lower energy. So the back bonding is making the dxy, dxz, and dyz orbitals more stable because their electrons can now attract to more nuclei. So in our energy diagram, the three lower orbitals are going to do this. And what does that do to the splitting energy? It increases the splitting energy. So the increased stability of the dxy, dxz, and dyz orbitals increases the splitting energy. So therefore, carbon monoxide is an example of a strong field ligand because it separates the energies of the two different levels of d orbitals. What do strong field ligands therefore have to have? They have to have empty pi antibonding orbitals, which means their Lewis structure has to have either a double bond or a triple bond in it. Now, if we do a complete analysis of a complex that has something like carbon monoxide as a ligand, this one here is hexacarbonyl ferrate 2, we can apply molecular orbital theory to it. And let me just show you that for a minute, although this is more of a graduate level type of analysis here. The iron atom in this particular complex has to have 6 d electrons, so its configuration is 3d6. How would molecular orbital theory handle the description of the bonding here? Well, you would have to have all the valence orbitals on the metal, and then the valence orbitals on the ligand interact with each other to form a whole series of molecular orbitals. So what I've shown here are atomic orbitals. The metal, the iron, has 3d atomic orbitals, a 4s atomic orbital, and some 4p atomic orbitals. The 6 different ligands will each have one orbital that has a lone pair in it, and they'll all be equal in energy. So I have the 6 different orbitals from the 6 different ligands shown on the left. The electrons that exist, there are 6 electrons in the metal, and then each ligand, those orbitals are the ones with lone pairs in it. They'll each have pairs of electrons. So if you can determine how the orbitals on the metal and the orbitals on the ligands will interact with each other by adding wave functions and subtracting wave functions, creating a whole series of molecular orbitals, you'll actually get 15 molecular orbitals of varying energies. The ones at the very bottom of the graph are bonding molecular orbitals. The ones at the very top of the graph are anti-bonding. And all the electrons from the metal and the ligands, and there are 18 of them, will fill the bottom orbitals up until you get to this point right here. Of this whole diagram here, which is based on molecular orbital theory and quantum mechanics, and this is the one I want you to focus in on this. See what's right here? 3 low orbitals, 2 high orbitals. If there's a big energy difference between those two sets, those final 6 electrons go into the lower 3 orbitals, and you have what's called a strong field ligand. Now, what's a weak field ligand? These are ligands that produce repulsion between ligand orbitals and the metal d orbitals, and it causes the splitting energy to be actually, I should say, small instead of large. That's a mistake there. So it should cause the splitting energy to be small. The types of things that are weak field ligands are things that have lone pairs in their outer shell, and most commonly are halogen ions, iodide, bromide, chloride, and fluoride. And let's see why that is. A chloride ion whose Lewis structure looks like this shows that it has lone pairs in its outer shell. There'll be a lone pair in a 3s orbital, a lone pair in a 3px, a lone pair in a 3py, a lone pair in a 3pz. Let me just draw one of those there. Now, if a metal approaches this ligand, and this is a p atomic orbital on the chloride, if a metal approaches it with one of its d orbitals in which the d orbitals point into the quadrant, not along the x or y or z axes, what's going to happen between the lone pair of electrons in the chloride ion and the pair of electrons in the dxy atomic orbital on the metal? They're going to cause repulsion. So if they cause repulsion, that's going to cause the energies of the dxy electrons to increase. And the same for the dxz and the dyz. So both the d orbital of the metal and the p orbital of the ligands contain electrons. That causes them to repel, and that's going to make the dxy, dxc, and dyz orbitals less stable because repulsive energy means higher energy. So the repulsion makes these three orbitals less stable. What does that do to the diagram here? It's going to cause the three lower d orbitals to have their energy raised, and you're going to wind up having a smaller splitting energy. So the decreased stability of the dxy, dxc, and dyz reduces the splitting energy, and therefore a chloride ion or any ligand that has lone pairs in its outer shell are going to wind up being weak field ligands. And if we apply molecular orbital theory to this for a complex that has a weak field ligand like a chloride ion, this one being hexachloroferrate 2, the iron here has 6d electrons. Once again, molecular orbital theory analyzes how all the atomic orbitals on the metal and the atomic orbitals on the 6 different ligands are going to interact with each other to form a series of molecular orbitals. And when they do, they'll form all these different molecular orbitals we saw before. Low energy ones are bonding orbitals, high energy ones are anti-bonding orbitals. The 18 electrons will fill in here, but once again, the only thing I want to focus in on is right here. If the splitting energy between these two levels is really, really small, then the 6 electrons will spread out over all 5 orbitals instead of only filling the bottom 3. So with a small splitting energy, you get the electrons spread out, and so a weak field ligand causes a small splitting energy. So let's even apply some of this. Let's take hexafluorocobaltate 3, and let me ask you a series of questions about this. First, could you give me the electron configuration of the cobalt ion that's in this complex? Well, the periodic table will give you the electron configuration of a cobalt atom. Chromium is located in the D block on the periodic table. It's in the first row of the D block. Those are the 3 Ds. And it's the 7th element over in the 3D block, so it's going to end 3D7 in terms of its electron configuration. If you go up 1 in the periodic table and all the way over to the right, you get to the element argon, so you can write argon in brackets, and then only name the orbitals get filled past argon, which would be the 4s, which would be 4s2, and then the 3D, which would be 3D7. So a cobalt atom's electron configuration is argon in brackets, 4s2, 3D7. Because the name says cobaltate 3, that means the cobalt is a positive 3 ion, so I have to pull 3 electrons off of this to get the electron configuration of the ion. And when you pull electrons off of metals, you always pull electrons off of the highest energy level first, and the 4th energy level is higher than the 3rd. So the 2 4s electrons get pulled off, and then to make a positive 3 charge, you pull one of the 3 Ds off, leaving argon in brackets 3D6. This is an important thing to be able to do because you need to be able to count how many d electrons you're going to have in your complex. And in this case, the central metal is going to have 6 d electrons. Something else you should be able to do is identify the ligands as strong field or weak field. The ligands in this, it says hexafluoro, are fluoride ions. Fluoride ions have lone pairs in their outer shell. Lone pairs create weak field ligands, and so they're going to make a small splitting energy. If we draw the splitting pattern now, the splitting energy is going to be really small because the ligands are weak field ligands. And if the splitting energy is really small, then now when we place the 6 electrons in there, they're going to spread out over all 5 orbitals first before they start to pair up. So 1, 2, 3, 4, 5, and then 6 at the bottom. This would be the splitting pattern for the cobalt in this particular complex. Now, is this complex high spin or low spin? For 6 electrons, if you spread them out over all the orbitals, you're going to maximize the number of unpaired electrons, so that's going to be a high spin complex. Is it paramagnetic or diamagnetic? Because it has unpaired electrons, it has to be paramagnetic. Let's try another one. Hexacarbonyl iron 2. If I ask you the same questions, first give the electron configuration of the ion in this complex. First, we'd have to determine the electron configuration of the atom. The iron atom is located in the D block of the periodic table, first row of the D block, so it's going to end in the 3D sublevel. It's the 6th element over, so it's going to end 3D6. So if we write argon in brackets, the only sublevels that are filled past argon are the 4s, which you go 4s2, and then you get to the 3D, you'd write 3D6. Because the charge in the name of the complex is 2, that means the iron ion must be positive 2, so we remove 2 electrons, and we always remove them from the highest energy level, so the 4s electrons get removed, so the iron positive 2 ion must be argon in brackets 3d6. Are the ligands in this complex strong field or weak field? The ligands are carbonyls, which is the fancy name for carbon monoxide, and that's a ligand that has either a double bond or triple bond in it. In fact, it has a triple bond. If you have triple bonds or double bonds, you're going to have pi bonding molecular orbitals, and more importantly, you're going to have pi anti-bonding molecular orbitals, which are empty, which are going to cause the ligands to be strong field. If we're going to draw the splitting pattern for this, because it's a strong field ligand, you would show a large energy difference between the lower set of d orbitals and the higher set of d orbitals. Therefore, the electrons will fill the lower 3 orbitals completely before they even think about going up into the higher orbitals. So on the bottom, 1, 2, 3, and then you fill up the bottom, 4, 5, 6. This would be the splitting pattern for this particular complex. Is it high spin or low spin? Because all the electrons are filling in the low orbitals, you have minimized the number of unpaired electrons, so there aren't any of them in this case. It's low spin. Is it paramagnetic or diamagnetic? Because there are no unpaired electrons, this would be a diamagnetic complex. So comparing the 2 complex ions we've just analyzed, the hexafluorocobaltate 3 would have a small splitting energy, so the electrons, the 6d electrons in the cobalt, would spread out over all 5 orbitals. But our second complex, because it has a strong field ligand, has a big splitting energy, so the electrons stay down in those lower, more stable orbitals like this. Now, back in Chem 1A, when we did experiments on flame tests, you would take a chemical, usually metal ions, you'd put them into the Bunsen burner flame, and the Bunsen burner flame would turn red or violet or blue or green, you get these cool colors. What was happening is you were using the Bunsen burner flame to add energy to the electrons in the metal ions. The electrons would jump to high energy states, and when they drop back down, it just so happens they emitted photons that fit in the visible region of the electromagnetic spectrum, so they emitted a color. In complex ions, a lot of times the difference in energies between the lower set of d orbitals and the higher set of d orbitals is in that visible region of the electromagnetic spectrum, so they can actually absorb some part of the spectrum, therefore they can be colored. So any complexes can absorb electromagnetic radiation, and if they do, you can promote electrons from the lower set of d orbitals into the higher set of d orbitals. When those electrons in the higher set of d orbitals eventually fall back down, because they will, then they will emit a photon of light equivalent in energy to the splitting energy. And if that photon happens to be in the visible spectrum, it's going to be emitting visible light, and you're going to see it as a colored component. Now, how is the splitting energy related to the color you might see? Well, the splitting energy is going to be the energy of the photon released when an electron drops from the high d orbital to low d orbital. So the energy of that photon is E. And from our electromagnetic radiation equations from Chem 1a, the energy of a photon equals Planck's constant multiplied by its frequency. Now, we know that the frequency of a photon is related to its wavelength because frequency times wavelength equals speed of light. If I take my second equation here and I solve it for frequency by dividing both sides by the wavelength, then the frequency of a particular photon is going to be its speed of light over its wavelength. I'm going to take c over lambda and I'm going to substitute it into the equation on the very left, and I'm now going to have a relationship between the energy of a photon and its wavelength. The energy of a photon equals Planck's constant multiplied by the speed of light divided by what the wavelength is. So that energy now of a photon that's emitted when an electron drops from a high d orbital to a low d orbital, if that photon that's emitted happens to be in the visible spectrum, then the complex is going to wind up being colored, and quite often that's the case. Now, for these two complexes we have at the top of the screen, experimental data has shown from spectrometers that the first complex absorbs electromagnetic radiation with a wavelength of 6.5 times 10 to the minus 7th meters. This is something that if you were in lab, you could actually do. You stick a sample of the hexafluorocobaltate 3 into a cuvette, place it into our spectrophotometer, and then you actually have the spectrophotometer shoot every single wavelength of light through it, and it makes a spectral graph of the absorbance of all different wavelengths. And you would see for the first substance here, there'd be a peak absorbance at 6.5 times 10 to the minus 7th meters, which is 650 nanometers. So in like 5 seconds, you could determine the wavelength of maximum absorbance of 6.5 times 10 to the minus 7th meters for the first one. If you take the second complex, put it in a cuvette, place it in our spectrometer, it's going to show you from a full spectrum graph that its peak absorbance is 4.5 times 10 to the minus 7th meters, or 450 nanometers. So if you know that, we can actually predict what color each of these substances would be theoretically, and then see if it matches experimentally. So if you're absorbing electromagnetic radiation with a wavelength of 6.5 times 10 to the minus 7th meters, which is 650 nanometers, on this scale, 650 nanometers is in the red region. So that means this absorbs red light. If it absorbs red light, what's it going to look like? Or if maybe it's orange, kind of reddish orangish there, right? So if it absorbs red or orange light, what color does it look like? Well, it looks like the complement of that. What's the complement of red? Green. What's the complement of orange? It would be blue. I think 650 actually fits more in the red region. So the complementary color would be green. So if the first complex is absorbing photons of red light, it's going to look green. And in fact, a solution of hexafluorocobaltate 3 is a green solution. For our other substance, it's absorbing wavelengths of 450 nanometers. What color is that? 450 nanometers looks like it's in the blue region. So if it's absorbing blue wavelengths, it's going to appear as its complementary color, which we would predict as orange. And in fact, a solution of that second complex is indeed orange. Now, can we calculate the splitting energies of each of these? You can if you know what wavelength it takes to promote electrons. So the wavelength of maximum absorbance equals the wavelength needed to promote an electron, and that wavelength is going to be related to the energy of the photons needed to do that. The energy of the photon will be the splitting energy. So for our first complex, we'll need to look up Planck's constant and the speed of light, and we'll divide them both by the wavelength of 6.5 times 10 to the minus 7th meters. So Planck's constant, 6.626 times 10 to the minus 34th joule seconds. Speed of light, 2.9979 times 10 to the 8th meters per second. And the wavelength that we measured as the maximum absorbance was 6.5 times 10 to the minus 7th. This means the energy of photons absorbed would be 3.1 times 10 to the minus 19th joules. And if it takes that amount of energy to absorb a photon, that is the splitting energy for that first complex. We could do the same thing for the second complex. The only difference is it absorbs a wavelength of 4.5 times 10 to the minus 7th meters. Meters cancel out, seconds cancel out, answer comes out in joules. And so the splitting energy for our second complex would be calculated to be 4.4 times 10 to the minus 19th joules.